Hello everyone, welcome back to another insightful video in our PySpark series. Today we are exploring a key concept in PySpark, the lineage graph. If you've ever wondered how PySpark can recover from failures without losing data or computation, the lineage graph is the answer. It's a powerful mechanism that ensures fault tolerance in distributed computing. Stick around as we break down what a lineage graph is, how it works, and why it's critical for robust big data processing. Introduction. In PySpark, a lineage graph is a logical representation of the sequence of transformations applied to an RDD to produce the desired output. It records every step in the data processing pipeline, from the initial data source to the final data set. This graph serves as an execution plan, outlining how data is derived and ensuring fault tolerance. If a partition of data is lost due to a node failure, Spark uses the lineage graph to recompute the missing data by reapplying the transformations from the source, eliminating the need to checkpoint every intermediate result. This mechanism makes the lineage graph a cornerstone of Spark's efficient and robust distributed computing framework. What is a lineage graph? Lineage graph in PySpark is a directed acyclic graph DAG that captures the logical relationships between RDDs and the transformations applied to them. It is a critical component of Spark's execution model as it provides a blueprint of how data flows through the series of transformations in a computation pipeline. Unlike data structures that store actual data, a lineage graph only describes the dependencies and operations, allowing Spark to optimize and manage distributed computations efficiently. Every transformation in Spark, such as map, filter, or groupie, creates a new RDD. Spark records the relationship between the parent RDDD and the resulting RDD in the lineage graph, forming a chain of dependencies. For example, when a transformation like map is applied to an RDDD, Spark updates the lineage graph to reflect that the new RDD depends on the output of the previous RDD. This process continues for every transformation, constructing a logical plan that Spark can later execute. The lineage graph is crucial for fault tolerance. If a node or partition fails during execution, Spark does not need to restart the entire job or retain intermediate results. Instead, it uses the lineage graph to recompute the lost partitions by reapplying the transformations from the original data source. This approach ensures data consistency and minimizes storage overhead while maintaining efficiency. Key characteristics of a lineage graph. The lineage graph in PySpark has several key characteristics that make it integral to Spark's distributed computing model. These features ensure efficient execution, robust fault tolerance, and streamlined resource management. First, the lineage graph acts as a logical execution plan representing the relationships between transformations applied to the data. It does not execute any computations until an action is triggered, such as collect or show. Instead, it records the sequence of transformations in a directed acyclic graph DAG, outlining how the data flows and how it should be processed. This deferred execution allows Spark to optimize the computation plan before performing any actual work. Second, the lineage graph plays a crucial role in fault tolerance. If a partition of an RDD is lost due to a node failure or other issues, Spark does not need to recompute the entire dataset. Instead, it uses the lineage graph to identify the exact transformations that need to be reapplied to regenerate only the lost partitions. This targeted recomputation minimizes overhead and ensures efficient recovery in distributed systems. Finally, the lineage graph leverages lazy evaluation, a fundamental concept in Spark. Transformations are not executed immediately but are added as dependencies in the lineage graph. Only when an action is invoked does Spark execute the transformations, optimizing the plan by reordering or combining operations to reduce data movement and computation costs. This lazy evaluation strategy ensures that resources are used effectively and computations are performed only when absolutely necessary. Together, these characteristics make the lineage graph a cornerstone of PySpark's efficiency and reliability. Example of a lineage graph. This example demonstrates how PySpark constructs and utilizes a lineage graph to manage transformations and actions in a distributed data processing pipeline. The process begins with the initialization of a Spark session, the entry point for executing Spark applications. An RDD resilient distributed dataset is created from a Python list of tuples using the parallelize method. This dataset represents employees and their respective ages, and it serves as the initial input for the transformations. At this point, Spark generates the first node in the lineage graph, representing the original dataset. The first transformation, filter lambda xx1 greater than 25, filters out records where the age is less than or equal to 25. This operation creates a new RDD underscore filtered that contains only the record satisfying the filter condition. The lineage graph is updated to reflect the dependency of RDD underscore filtered on the original RDD. Next, the map lambda xx0 x1 multiplied by 2 transformation creates another RDD underscore map by doubling the age values of the filtered records while retaining the names. This transformation adds another node to the lineage graph, linking RDD underscore map to RDD underscore filtered. Throughout these transformations, no actual computation is performed due to Spark's lazy evaluation. Instead, Spark constructs a logical plan in the lineage graph. The computation is triggered when the collect action is invoked on RDD underscore mapped. At this point, Spark executes the operations recorded in the lineage graph, applying the transformations in sequence to produce the final output. The results are collected back to the driver program, which prints Alice 60, Charlie 70, representing the transformed dataset. This example highlights how PySpark efficiently manages data transformations using the lineage graph. By deferring execution until an action is called, Spark optimizes the computation plan and ensures fault tolerance by tracking dependencies between RDDs. If any partition of data is lost, Spark can use the lineage graph to recompute only the necessary partitions, making the framework both robust and efficient. Lineage graph for the example. The initial RDD represents the starting point of the data processing pipeline. It is created using the parallelize method, which takes a Python list of tuples and distributes the data across partitions in the cluster. At this stage, the RDD is simply a representation of the original dataset and no computations have been performed. Spark records this as the first node in the lineage graph. The filtered RDD underscore filtered is created through transformation 1, which applies a filter operation. This transformation selects only the records where the age is greater than 25. When this transformation is defined, Spark adds a new node to the lineage graph. This node records the dependency of RDD underscore filtered on the original RDDD and documents the filter condition applied. However, due to Spark's lazy evaluation, the actual filtering does not occur at this point, it is merely registered in the lineage graph. The mapped RDD underscore mapped is produced through transformation 2, which applies a map operation. This transformation doubles the age values while retaining the names from the filtered RDD. Similar to the filter operation, Spark adds another node to the lineage graph, capturing the dependency of RDD underscore mapped on RDD underscore filtered and documenting the mapping logic. Again, no computation is performed at this stage as the transformation is only recorded in the lineage graph. The action collect triggers the execution of the lineage graph. When collect is called, Spark processes the data by executing the transformations in the recorded sequence. The filter operation is applied first, followed by the map operation to produce the final result. This result is then collected back to the driver program, where it is displayed as Alice 60 Charlie 70. This step by step process illustrates how Spark builds and executes a lineage graph. By deferring computation until an action is called, Spark optimizes execution, minimizes redundant processing, and ensures fault tolerance by maintaining a detailed record of transformations and their dependencies. If any partition of the data is lost, the lineage graph allows Spark to recompute only the affected partitions, making the framework both efficient and resilient. Fault tolerance and lineage graph. The lineage graph is a cornerstone of PySpark's robust fault tolerance mechanism, ensuring data reliability in distributed environments. Its primary role is to record the dependencies between RDDs, forming a logical blueprint of how each RDD is derived from its parent S. This detailed record allows Spark to understand the sequence of transformations and operations applied to create the final dataset. In the event of a partition loss, such as a node failure in the cluster, Spark leverages the lineage graph to recompute only the lost partition. It achieves this by reapplying the transformations recorded in the lineage graph on the parent RDS that contribute to the lost data. For example, if a node containing a partition of filtered data fails, Spark retraces its steps to the original RDD and re-executes the transformations e.g. filter map to regenerate the lost partition. This mechanism ensures efficient recovery as Spark avoids reprocessing the entire dataset and focuses solely on the affected partitions. By limiting the computation to the necessary portions of data, Spark minimizes resource usage, reduces downtime, and maintains high performance even in the face of failures. This capability, enabled by the lineage graph, makes PySpark highly reliable and suitable for processing large-scale distributed datasets where hardware failures are not uncommon. Example of fault tolerance. This example demonstrates the concept of the lineage graph in PySpark and its role in tracking the transformations applied to RDDs. The process begins with accessing the existing Spark context, which serves as the entry point for all operations in PySpark. Using this context, we create an RDD from a Python list of numbers 1, 2, 3, 4, 5, 6 by calling the parallelize method. The numSlices 2 parameter ensures that the data is divided into two partitions, allowing for parallel processing across the cluster. Next, we apply a transformation to the RDD using the map function. This transformation squares each element of the RDD, creating a new RDD underscore transform that contains the squared values. Transformations in PySpark, such as map, are lazy, meaning they do not immediately compute the result but instead record the operation in the lineage graph. This graph captures the dependency of RDD underscore transformed on the original RDD, ensuring that Spark knows how to recompute it if needed. To execute the transformations, we invoke the collect action on the transformed RDD. This triggers Spark to compute the transformations recorded in the lineage graph, process the data in each partition, and return the results to the driver program. The output 1, 4, 9, 16, 25, 36 represents the squared values of the original dataset. Finally, by calling toDebugString on the transformed RDD, we view the lineage graph. This method provides a textual representation of the RDD's dependencies and the operations applied to it. The lineage graph shows the steps Spark recorded to produce the final RDD, such as the number of partitions and the transformations applied. This visualization is crucial for understanding the data flow and optimizing Spark applications. In summary, this example highlights how PySpark tracks transformations in the lineage graph, executes them only when an action is triggered, and provides insights into the data processing pipeline for efficient debugging and optimization. Advantages of lineage graph in PySpark. The lineage graph in PySpark provides several critical advantages that make it a cornerstone of Spark's distributed computing model. These advantages ensure that PySpark applications are efficient, reliable, and easy to debug, even in complex data processing scenarios. One of the key benefits of the lineage graph is its role in fault tolerance. In distributed environments, failures such as node crashes or data loss are common. The lineage graph enables Spark to efficiently handle these failures by recomputing only the lost partitions of data. Instead of restarting the entire job, Spark uses the dependencies recorded in the lineage graph to retrace the steps and regenerate the missing data from the original source or intermediate transformations. This ensures the reliability of Spark applications without introducing excessive overhead. The lineage graph also plays a pivotal role in optimization. By recording the logical dependencies between transformations, Spark can analyze the graph to combine multiple narrow transformations, e.g., map filter into a single stage. This reduces unnecessary data shuffling and minimizes the number of stages, leading to faster and more efficient execution. This optimization ensures that Spark makes the best use of cluster resources while processing large data sets. Another advantage is the transparency it provides. Developers can use tools like Buckstream to visualize the lineage graph and understand the sequence of transformations applied to the data. This makes it easier to debug issues, optimize the data pipeline, and ensure that the application is performing as intended. By providing a clear logical execution plan, the lineage graph allows developers to identify bottlenecks, inefficiencies, or potential errors in the data processing workflow. In summary, the lineage graph enhances fault tolerance, enables execution optimizations, and promotes transparency, making it an essential feature for building robust and efficient PySpark applications. These advantages contribute to PySpark's popularity as a framework for processing large-scale distributed data sets. That's all for today's deep dive into the lineage graph in PySpark and its role in ensuring fault tolerance. We hope you now have a clear understanding of how PySpark uses lineage to recover lost computations and manage distributed data efficiently. If you found this video helpful, don't forget to like, share, and subscribe to our channel for more PySpark tutorials. Drop your questions or thoughts in the comments below. We'd love to hear from you. Until next time, keep learning and exploring PySpark.